Good morning, friends. Now we are discussing conservation of mass, velocity, potential function, and stream function in module number 2 of fluid mechanics. What is law of conservation of mass says? So, in simple words, we can say that the mass is neither created nor destroyed in any system, but it will be transformed from one form to another. So, whatever chemical reaction taking place, so mass of any one element at the beginning of the reaction will be the same as the mass of that particular element at the end of the chemical reaction. Continuity equation. So is based on conservation of mass law. So here I am considering two cross sections of the pipe here, section 1 and section 2. So V1 is the average velocity at section 1. Rho 1 is the density of the flowing fluid, and A1 is the cross sectional area of the pipe at section 1. See, we can see that there is a gradual increase in the diameter of the pipe. So from section 1 to section 2, so there will be change in the diameter. So V1, rho 1 and A1 will be the velocity, density and cross-sectional area of the pipe at section 1. So V2, rho 2 and A2 will be the corresponding values at the section 2. So the rate of flow now at the section 1 is rho 1 into Q1. So that is the discharge. So that is the discharge is given by the equation Q is equal to A into V, area into velocity. So area is in meter square, velocity is in meter per second. So discharge is in meter square into meter per second. So meter cube per second. That is the quantity of water flowing through the particular section per unit time. So the rate of flow now is given by density into discharge. So rho 1 into A1 into V1. Similarly, the rate of flow at section 2, it is rho 2 into A2 V2. So according to the law of conservation of mass, we say that the flow rate at section 1 will be equal to the flow rate at section 2. So it is rho 1 A1 V1 is equal to rho 2 A2 V2. If the fluid considered is incompressible, so the density remains same. We cannot compress the liquid, so density remains same. Rho 1 is equal to rho 2. So they get cancelled with each other. We have A1 V1 is equal to A2 V2. So this is continuity equation. Now velocity potential function. So the velocity potential function is the scalar function of the space and time. So here we are considering the space coordinates x, y and z such that this velocity potential function, which is denoted by the symbol phi here, if we take the negative derivative of this function phi with respect to any direction, maybe x, y or z, will give the fluid velocity in the particular direction. So velocity potential function phi, its negative derivative with respect to the x direction will give the velocity, fluid velocity in the direction of x, that is given by u. So u is the negative derivative of this velocity potential function phi with respect to the space coordinate. So that is x. So gives the fluid velocity in the particular direction. So u is minus of del phi by del x, v is minus of del phi by del y, w is equal to minus del phi by del z. So u, v and v are now the velocity components in x, y and z directions respectively. So mathematically the velocity potential function is given as f of x, y, z for the steady flow. So now to get the fluid velocity in the direction of x, we have to take the negative derivative of this function with respect to the direction x. Similarly, v and w will be obtained. So the continuity equation for any incompressible steady flow is given by del u by del x plus del v by del y plus del w by del z is equal to 0. So in Cartesian coordinates, so this is the equation, del u by del x plus del v by del y plus del w by del z is equal to 0. Substituting the values of this u, v and w, the velocity components in x, y and z directions. So in place of u, substitution is del phi by del x with negative sign. V, we have minus del phi by del y. W, minus del phi by del z as we have here. So the same thing is substituted in place of u, v and w. So we have minus of each quantity here with the square here, del square phi by del x square, del square phi by del y square, del square phi by del z square. Taking minus 1 outside and to the right side, 0 divided by minus 1 is 0. So this equation is called as Laplace equation. Then stream function. So the stream function is the scalar function of the space and time. So the stream function is denoted by the symbol psi. So the scalar function of space and time such that its partial derivative with respect to any direction. So if you take the partial derivative of this psi with respect to x, it gives the velocity components at right angles to that direction. So it's del c by del x. So taking x direction, so right angle to x is y direction. So velocity component in y direction is v. So taking the partial derivative of this function psi with respect to x direction will give the velocity component at right angles to that direction. X direction's right angle is y direction, their velocity component is v. And it is defined only for two-dimensional flow. So that's why only x and y are shown here. So del c by del y is equal to minus u. So psi is function of x comma y. Thank you friends.